Hi, I'm Beth Wilson. I'm one of the hosts of STEM in 30, a science program for middle school students that is produced at the National Air and Space Museum. Today, I'm really excited about our live chat. We are joined by what I'm calling the Hubble Telescope All-Stars. To begin with, we've got Dr. Jennifer Wiseman, who is the Hubble Space Telescope Senior Project Scientist. We have Lou Strolger, observatory science at the Space Telescope Science Institute, and Mike Massimino, NASA astronaut who worked on several of the Hubble missions. Thank you all for joining us. I've got a couple of questions that'll get us started. Jennifer, your primary responsibility is to ensure that the Hubble missions are as scientifically productive as possible. We have an image of one of the latest images of Hubble that we're showing the public. Can you briefly tell us about this latest photo and what it tells us about our universe?
Sure. Well, I'm super excited to be on this program. This year, we're celebrating the 30th anniversary of the Hubble Space Telescope mission. It was launched from the space shuttle 30 years ago, and it's been operating ever since. It's still in great shape. We're excited about that. I work with lots of people on the ground who are experts at keeping Hubble fit and doing great science. So thanks to them, this large Hubble team, we've got a good facility. And that image is one we just released to celebrate Hubble's 30th birthday. It's a beautiful region in a little satellite galaxy to our own Milky Way. And in this region, stars are still forming. So you can see a beautiful red nebula. There are massive stars in the middle of that nebula that are more than 10 times more massive than our own sun. And those stars are so energetic that they can send out light that ionizes the surrounding gas that produces these beautiful colors. And it also tells us something about the nature of that gas by the different filters we use on the Hubble telescope. So the blue color tells us that there's really heated oxygen in that gas, and the red colors give us indication of nitrogen and hydrogen. And in the bottom part of this image, you see a big kind of blue puffy cloud. That's a nebula that's emitted from just one great big star that's several 100,000 times brighter than our sun. It's a special kind of star called the Wolf-Rayet star. And every once in a while, it ejects part of its atmosphere. And what you're seeing is some of that heated emission from the last sort of eruption from this star. And so all of this region tells us that our universe is very dynamic. There's still a lot of activity, still a lot of stars forming, still a lot going on. And it also tells us that the Hubble Space Telescope is able to get us beautiful images that we really wouldn't be able to see just with our naked eye, because Hubble is up above the atmosphere of Earth, so it can get really sharp, beautiful pictures like this one.
I want to remind everybody that we will be taking questions. Put them in the comment section. We will get to as many as possible during our time here. Lou, can you tell us about how the Hubble projects are determined, and also talk a little bit about the dual anonymous evaluation project process that you all have adopted, and how that sort of changed what sort of projects you're doing now?
Sure, no problem. Thank you for inviting me to be here. It's great to be
Oh,
here.
yeah, that's great.
So every year we receive something like 1,000 proposals from different scientific investigators throughout the whole world on what they would like Hubble to do in the upcoming year. Um, each year that what Hubble's capable of actually observing is something like 200 of those. So there has to be a down select at some level. We invite upwards of 150, and now it's closer to 200 investigators throughout the world to review those proposals and give us their recommendations as to what is the most meritorious. What should we spend this year using Hubble on? Um, those investigations, as Jennifer just alluded to, are highly wide ranging. And it has been highly successful, but it is highly competitive. And part of that, with any competitive process, you have biases that tend to creep in to the selection process, whether that be conscious or unconscious. A few years ago, we were doing a study of our statistics, and we noticed that proposals led by female investigators were systematically lagging behind in terms of success rates their male counterparts. And that had us considerably worried. We also felt that that was sort of the tip of the iceberg. There could be a lot of unconscious bias in the selection of what things get done. So we decided, after much investigation, to go with a process that is largely anonymous, where the reviewers do not know who is proposing. And of course, the proposers don't know who the reviewers are until the end of the process, when things are selected by their scientific merit. We've found that that actually has been highly successful. We see evidence that the gender bias is indeed decreasing and coming back to closer to what we would expect. But we also see other biases that we didn't quite know of that are actually showing some evidence of success. The number of new investigators for the first time using or successfully getting time on Hubble has increased almost by a factor of 10. And that in itself tells us, about the vitality and the longevity of this mission. So we're highly excited about this dual anonymous process, and we've been trying to spread the word to as many other scientific investigative selection processes to try and get them and their peer review processes to adopt the same thing. And it's caught on like wildfire. A lot of people have been interested in it. So we're very proud of it. We're very happy that it's happening, and we look to continued success.
Great. Mike, you were on 2 Hubble servicing missions. One story that you tell that I've always really liked is you had to remove over 100 fasteners, but there was one stripped bolt that gave you a bit of a headache. Do you want to tell us about that servicing mission?
Yeah, and you're hearing me okay now? We're having a little technical issue before. But yeah, actually, not that I was counting, but it was exactly 111 small fasteners, plus 2 larger ones on a clamp and 4 on a handrail, for a total of 17 that needed to come out. 117 needed to come out. But out of that group, the 111 were very small fasteners. They were holding an access panel onto the Space Telescope Imaging Spectrograph, which is an instrument, what we called an axial instrument, which means it's about the size of a refrigerator or a telephone booth. And it had a power supply failure inside and wasn't working any longer, and we did not have a replacement. Generally on the servicing missions, what we did up till that mission, what we did was we would remove a piece of equipment. The way they built, it's hard enough to build a telescope, I would think, just to build it, but then they had to build it so it could be serviced by astronauts. So it needed handrails and doors that could open, and instruments could slide in and out, and all these interfaces. I mean, that makes it really tough. And even then, you got to consider astronauts are going to break things and do things wrong too. So you had to try to make it as astronaut proof as possible. They did a pretty good job on most of that. But when they put this instrument in, they never expected anyone ever to take it apart, which is why they had 111 astronauts holding this access panel on these little screws. And we did not have a replace. So up till that point, we generally would remove a piece of equipment. The whole thing would come out. You had fasteners and latches, and you'd pull it out. You slide a new one in and hook it up, and that's the way we did it. But we did not have a replacement for the STIS instrument, and we devised this very complicated spacewalk to take it apart. It was the most complicated spacewalk ever attempted, or at least one of them ever attempted in the history of the shuttle program. But we had so much experience and good experience with the Hubble team. We thought that we could pull this one off. Over 100 new tools were designed just for this task. And I go ahead and make I mess up the easiest thing on it, which was removing the handrails. It was simple, 4 big screws, and I stripped one of those screws. But the solution came up after a while for me to just tear this thing off, which was might sound simple, but it's not something we would normally do in space, because you can create debris and you can puncture your spacesuit. Plus, I mean, I didn't think of it. I was trying to think of what other parts of the instrument we could take apart, but I felt terrible about it that I had made this mistake. But luckily, the control team, it was some of the engineers at Goddard who came up with that idea and tested it. Right, well, it was a Sunday afternoon this was going on too, but they all rallied and came up with a solution. And the spacewalk went long. It was one of the longest ones we've ever had. It was over 8 hours, longest one I've ever had. But we got it done in the end.
Well, let me add to that, from the scientist perspective, Mike, we are so thankful for you and your team. Even with these problems that came up, you overcame them. Literally, I was praying in the control room all the time. You guys were terrific, and because of that, we have the STIS instrument still operating, the Space Telescope Imaging Spectrograph. It is truly unique. It is my favorite instrument on Hubble. It can do what we call spectroscopy, which is taking light and dividing it up into its constituent spectrum of colors. And that helps us to find the composition of things that we're studying, whether it's galaxies, stars, or the interstellar medium. It can also help us gauge the motions of stuff in space. So we're using STIS now to do amazing things like measuring the composition of exoplanet atmospheres, things like that, because of what you did. So thank you, Mike, and your team for doing that.
I'm certainly glad. I'm certainly glad I didn't break it.
Well, we're glad too, and we've got a lot of questions that are coming in now. Sona, Jonas, and Jen want to know, how far can you see with the Hubble telescope? Jennifer, maybe you can give us a quick answer on that.
Sure. So, we'd like to say something in terms of like how many miles or kilometers can we see out with Hubble, but space is so vast that becomes really impractical. So we use a unit of distance called a light year, which is basically the distance that light travels in a year. And even that gets a little cumbersome because we're looking so far out in space with the Hubble Space Telescope that we're seeing galaxies now that started, the light from those galaxies start millions of light years away or in the past, and sometimes billions. So I like to think of it this way. We think our universe is about 13.8 billion years old. And we're seeing light from galaxies that started its trek to us from within that first 0.8 of the 13.8 billion year history of the universe. So really in cosmic infancy or adolescence, we're seeing baby galaxies that are just starting to form just a few 100 million years after the Big Bang. So we're looking very far back in space and time because of the sensitivity of the Hubble Space Telescope and the James Webb Space Telescope, which will be launched next year. And we hope to have Hubble and Webb operating at the same time for a few years. That Webb telescope will be able to see even more distant or earlier galaxies, coming to us from the first few 100 million years of a 13.8 billion year universe. So that's how I would answer that question.
Okay. I'm going to combine this a little bit. Aaron, Wine, and Christine. Lou, want to know, what is the Hubble telescope made of? And how long did it take it to build? And then, Mike, if we can follow up on how many missions had to go to the Hubble telescope to keep it up and running for so long. So Lou, if you want to start with that.
Well, unfortunately, I don't know the answer. I would have said sugar and spice and everything nice. Maybe Mike and Jennifer could answer that a little better than I could.
Okay.
What the telescope is made of.
Yeah, Mike, do you want to take a shot at it?
What the telescope is made of?
Yeah.
It's got a bunch of different components. It's got it kind of split up into two major areas. One is we call the ash shroud, which is where the big instruments, I mentioned some of them earlier, the axial instruments are, and then above that is the forward shell light shield, which is the skinny part. So to me, it kind of looked like it was like a soup can on top of a tuna can, sort of. That's the way astronauts would describe it. And it had scientific instruments 4 of them about the size of a refrigerator, 4 of them about the size of a baby grand piano. Those are radial instruments, including the wide field camera. And then it had batteries and solar arrays and the mirrors inside. Well, as far as what the actual composition of those pieces were, I think it was a lot of composite material, lightweight material, and it's very, very shiny mylar on the outside. And not even just mylar, but just the whole, it's just a very shiny telescope. Very, very shiny. You could see your reflection very clearly while you're moving around it.
Lou, do you want to tell us a little bit about how that telescope works as opposed to, ones we have here on Earth?
Yeah, so there's, I think, 2 greatly unique things about that telescope that are differ from others that we typically use. The first, of course, Jennifer already pointed out that it sits above the Earth's atmosphere, which if you want to study high energy events or some events in the near infrared, just trying to understand how the most energetic objects in our universe behave, you really need to probe the ultraviolet area of the electromagnetic spectrum. And thankfully, our atmosphere does a great job of blocking that. So by putting a telescope way above that, we can, again, look at those high energy processes and be able to understand how Wolf-Rayet stars behave, for instance. The second is it's a robotic telescope. And a lot of people don't realize that, as much as we love to send people to service the telescope, we wouldn't want to send people to actually operate it, which would be a pain. So,
Oh.
so we send instructions to it on a weekly or even sub-weekly basis, and we receive the observations beamed back to us through a telescope network, through a communications network. So I think those 2 things make it a unique observatory, one where you have to, where you can do things that you wouldn't be able to do from the ground. And you have to think a little bit ahead as to what you want to observe.
Well, we have a lot of people watching from all over, from New Jersey, Pennsylvania, Indiana, England, Wales, Missouri, Sri Lanka, that's a new one, North Carolina, Brazil, West Virginia. So we've got a lot of people watching. And one of the questions that I'd like to ask all of you, because I'm sure you have differing opinions, and we'll start with Jennifer. What do you think Hubble's coolest or best discovery was? And Caitlin, Nate, and Michael want to know.
Oh, there are just so many
So
amazing things that Hubble has accomplished, but my personal favorite are these deep fields, like the ultra deep field. These are images taken by simply pointing Hubble in a direction of the sky that doesn't have any bright nearby stars to drown out the image, and just collecting light for several days so that in the end, the faintest objects will show up in the resulting image. And what shows up in the deep field are thousands of little smudges of light. These are galaxies outside of our own Milky Way galaxy. To me, that's just a wonderful visual revelation of how rich our universe is, filled with galaxies. Just imagining that extrapolated over the whole sky. That's the kind of incredible universe we live in that has hundreds of billions of galaxies in the observable universe. And then beyond that, of course, realizing that some of these galaxies are farther away than others. And so it's really like a time machine snapshot. We're seeing some galaxies as they were earlier in their own existence, and some galaxies closer to us in space and time, because it's taken time, vast amounts of time, for the light to travel to us from these different galaxies. So we can kind of map out how galaxies have changed over cosmic time by gauging carefully the distances to these different galaxies and seeing how the ones that are shining to us from earlier in the history of the universe compare to the ones that are more like our own Milky Way, more mature. And we see that galaxies have changed over time. They've merged together with other galaxies to grow bigger and more massive. And they've even had generations of massive stars come and go that produce heavier elements, so that galaxies like our own are now enjoying an enriched composition with elements like oxygen and iron, things we need for planets and life. So I love the ultra deep fields. That's my favorite.
Okay, Lou, what about you?
Oh, I'm highly biased. So there are great observations, great discoveries that Hubble has made over its 30-year history. But the one that it has contributed to that is the most impactful has been the discovery of dark energy. So I was part of a team of investigators that looked at how the universe is moving uh, sort of dynamically or kinematically, I should say, but how the universe is moving in different epochs in the past. And what we've learned is that the universe has been recently accelerating in its expansion, apparently being driven apart by dark energy. That discovery came from watching supernovae at different epochs in the past and how they appear relative to how we see them now. And that came largely from Hubble, being able to see the distant past and seeing how those supernovae differ significantly from the ones that we see now. And that's been the track of my career. That's what we continue to do. We look forward to things like James Webb and WFIRST to tell us even more about what dark energy is doing, not just its current strength, but its evolution over time.
Mike, what about you? Do you have a favorite that pops out?
What was just mentioned, I think, are probably my two tops, and part of the reason is because we were able to contribute to that in our way by putting the instruments in that made that possible. But I'll go back to my those are really the best. I mean, those are the great. If you want to learn something, listen to those two answers. But I think that that I would say from my perspective too, I'll just throw a whole different way to look at it. Two of my favorites from my first mission was the Cone Nebula, because it showed that the advanced camera for surveys was working. Yeah. And we installed that. I hooked it up on the first flight, so I was very pleased to see that it actually was. And it takes a little while for them to warm the telescope up again, and after we service it, we think we did a good job, but we're not always sure. But the Cone Nebula is the birthplace of stars. It's not the most significant, and maybe not even the most beautiful, although it is very beautiful. But for us, it was meaningful because it showed that the telescope was working. And then Jennifer mentioned the STIS image. The first STIS image I saw after we put that instrument back together was, it looked like a light bulb at the end of a tunnel. And that was that's one of my favorites. So just to give you a different perspective, we were so pleased that we got the telescope and the instruments working again, so that people like Lewis and Jennifer can make their discovery. So that's just, I guess, a different way to look at it. We were very happy to see that it was working with the early release images. But the discovery of dark energy is truly amazing, and that I would, it's a Nobel Prize winning discovery. So that has to be, I think, right up there at the top. And the ultra deep field, the more I look at it, the more I like it. So I like those two answers before. So
Abby would like to know, she read that when it was built, Hubble's pictures were fuzzy because the lens was off by a 500th of a human hair. Why did that affect it so much?
Yeah.
Well, Hubble was meticulously planned for decades. Actually, the idea had been percolating of what you could do if you could put an observatory in space above the blurring effects of the atmosphere. It was designed, every component was very carefully developed, including the mirror. It was very, very nicely polished. But it was discovered after Hubble was launched that it was very slightly misshapen, and that created something called spherical aberration in the images. It was such a slight issue in terms of the optics within Hubble, and yet because of the extremely high resolution of Hubble and its sensitivity, it did make a noticeable difference in the images. So this was an initial disappointment with Hubble, and really an embarrassment for NASA, right, when it was launched. But you know what? Hubble had already been designed to be paired with subsequent servicing missions from astronauts. So the whole team of engineers and technicians and ground managers and people just got really busy trying to figure out how, on the first subsequent servicing mission after the Hubble was launched, that maybe this optical problem could be fixed. And in fact, they devised a really ingenious solution, which is that all the newer cameras put on Hubble have a correction built in that compensates for the spherical aberration problem in Hubble's mirror and optics. And also for some of the instruments at first, there was this corrective lens, if you will, added onto Hubble called CoStar, that also performed some of those corrections. So it's kind of like putting corrective glasses on Hubble and for its instruments. And ever since that first servicing mission in 1993, the data coming in from Hubble are just spectacular. And in fact, some of the instruments from Hubble, including that corrective instrument called CoStar, have been brought back to Earth in subsequent missions and put in the National Air and Space Museum, so you can see some of these things on display.
When we reopen, they'll be there. Caden from Kansas would like to know, how far away from Earth is the Hubble telescope? And also, if we can combine two questions in that one, now that we don't have the shuttle, is there a way to do any repairs on it?
Well, I'll jump in and let the others jump in too. Hubble's about 350 miles, more or less, from the surface of the Earth. So it's in what we call low Earth orbit. That's the same orbit that the space shuttle could achieve. So that's why it's there. And it was revisited 5 times after its launch, after it was first launched by space shuttle missions. But we don't have the space shuttle operating anymore, as NASA is developing this new space transportation system that will take astronauts farther than the shuttle could. So back to the moon and hopefully even Mars. So right now we don't have the capacity to service Hubble with the shuttle, but we are in fact doing everything we can from the ground to make sure that Hubble is as productive as possible. There's a lot of things we can do from the ground if there are little technical glitches and things, different ways of commanding the telescope or using the gyroscopes and different mechanisms on Hubble. Even if there are some glitches, we have some workarounds, and we have an ingenious team of engineers and technical experts on the ground that are paying special attention to that. As far as other ways of servicing, we're not planning that within NASA right now, but I know there's some chatter outside of NASA of creative ways that might be able to be done. So I'll turn it over to our other folks. Mike, you got any thoughts on this?
Yeah, there's I guess the simple answer is we're not going to be able to service it any longer. We needed the space shuttle to do that because it could bring up equipment and bring equipment back, and it was ideally made for that. One of the tasks for the shuttle, Hubble was built to fit inside of the space shuttle, and so it's very doubtful that we don't have the space shuttle anymore. So if we're going to do it, we're going to have to do it with another spacecraft, and there's no funding for that. And as Jennifer has said, the telescope, the life of we got to Hubble at 30 now, right? That's pretty good. And when it first was launched, they were hoping for Hubble at 15 to make it to 15 years, and now it's already at 30. And as Jennifer said, the great people on the ground keep it going. But we did attach a docking ring to the bottom of the telescope. It was a high priority. It was done on our first spacewalk on the last mission. And that docking ring, the intention for that is, the reason it's up, it was important to get it on there, is that eventually Hubble's orbit is going to decay. And as it decays, they want to be able to send up a rocket motor to attach to guide it back safely to Earth, where most of it will burn up in the atmosphere, and any big pieces that make it through will come down harmlessly in the ocean. So there is a docking ring there that someone maybe could dock to and maybe reboost it and keep it going. So it's not that it's impossible. It's just that you're gonna have to be really creative using some other spacecraft, and the Orion spacecraft or something. It's not gonna be as easy as not that it was easy with the space shuttle, and there's no funding and there was no intent to do that. So probably we're very close to zero, but I would never count out the Hubble.
Yeah, I would absolutely. This is 350 miles seems like such a long distance, but it's really not that far away. And this thing has been incredibly productive for such a very long time, and is still so overly subscribed. As I said, 1 in 5 proposals actually get time every year to observe on this telescope. So the scientific return is still high. It would be a shame if we didn't return to this observatory, this highly productive observatory in the next few years, and it continue to extend its lifetime. Make it, there have been some transformative observatories on the ground that are still operating. I don't see any other reason why Hubble can't be in that same regime.
Okay, Teddy, who is 4, would like to know why do these telescopes use mirrors and how do they work?
So very good question. So the answer is that there's typically 2 ways in which you can focus light into a smaller point so that you can use it as a telescope. You could do this refractively, looking through a lens, but that has its own issues that include something called chromatic aberration, which makes light of different wavelengths focus at different points. Mirrors don't have that problem. They actually focus all the light at the same point. And they also allow for a much more compact design. You can focus the light back in the direction from which it came. So as big as Hubble is, I guess it's as big as a school bus. It's a lot more compact than it would have been if it had been a refractor. So that's the reason why it's designed the way it is.
Okay. Mike, someone is reading your book and wants to know the difference between a spacewalk on Hubble and one on the International Space Station.
Well, all right. So the thought went into my head, so I have to say it. But one of my colleagues got in trouble for this, and he was asked. He spacewalked with us on Hubble, and he was assigned to a spacewalking flight on the International Space Station. And Lou and Jennifer, you might get a kick out of this, but he was asked, "What's the difference between spacewalking on Hubble and spacewalking on the International Space Station?" No disrespect to the International Space Station, but what he said was he felt like on Hubble he was doing brain surgery, and on the International Space Station he was doing landscaping. So no disrespect to anyone, but Hubble was very intricate in what we were doing, and we had to be it was very delicate work. We had to be really careful about what we touched, particularly when the telescope was exposed, meaning the doors were open. We had to be really, really careful about what we were doing inside of there. With the space station, not encouraged to be rough, but it's a little bit tougher. You can be a little bit rougher with it and probably get away with it, but you could not get away with that on Hubble. And I think the other major difference was that on Hubble, we knew, especially on that last mission, we knew we were going to be the last folks there. I mean, we talked about maybe having astronauts go again, but that's probably not going to happen. And we were thinking that is definitely not going to happen. And we tried to jam pack everything we could into those spacewalks. And we knew that whatever didn't get done was not going to get done. Whereas on the space station, it doesn't have that same urgency typically, because you always have a crew on board. Even when we were assembling the space station, we have crews coming to visit. If something can't get done that day, you'll come back next week. You can go out again. So it's not that same urgency. So I think the 2 biggest differences were that we had to be very delicate handling the spacewalking on the telescope, and we were really trying to pack as much as we could in those days that we were spacewalking.
Okay, we've got a lot of people still watching from Oregon, California, Mexico, Virginia, Arkansas, New York, Washington, Scotland, and Montana, and the Ukraine. And somebody wants to know about my cat astronaut behind me. It's hiding a nail in the wall. So that's why that's there. One of the questions, I thought this was really interesting, and Jennifer, I think you can probably answer it. Liz wanted to know, how long does it take for a star to form?
Oh, that's a great question. So stars are actually just basically compressed balls of gas. Our galaxy has a whole lot of this, what we call interstellar gas, the interstellar medium. And sometimes it's pretty turbulent, but sometimes you'll get a little pocket of this stuff that's pretty dense. And so its own gravitational pull will be more powerful than the turbulence that might disperse it. And if you have enough material falling in on itself due to its gravitational pull, it can create a very high pressure ball of gas, basically. And if there's enough mass, that pressure will be high enough to ignite a process called fusion in the core of that little ball of gas. And fusion is a reaction or a series of reactions that eventually produce light that is released outside of this ball of gas. And that's what a star is doing. That's what our sun is doing. Now, this whole process of taking a big cloud of interstellar gas and having it transform into this collapsed or collapsing set of balls of gas that become stars takes differing amounts of time depending on how much mass is in these regions. So the most massive stars actually form the quickest. They can form in, maybe a million years, a few million years. But for lower mass stars, it can take much longer than that. So it depends on the mass of the star, the time frame by which it forms, and not only that, but the time frame by which it continues to shine as a star. So the most massive stars form the fastest, but they also burn out the fastest. A few hundred million years, whereas a star like our sun can go on for billions of years. So it's kind of like live fast, die hard kind of thing for stars.
We've got to really, I love these sorts of questions. What advice would each of you have for young people watching who aspire to become astronauts, astrophysics, and other kinds of scientists? So Lou, let's start with you and we'll.
Oh, I think my number one advice is perseverance. It's so easy for these sort of dreams and these sort of ambitions to die young, as you will, because there's so many other things in which could attract your attention, whether it be issues. I mean, uh, right now we have issues of social injustice and things that are very important to young folks that I think people should pay attention to. However, it's also very hard to stay the course and see through your dream of becoming an astronaut or an astrophysicist. And the only way to really see through that is to persevere, to keep that dream alive, keep that hope alive, and keep going through even when classes get tough or times get tough.
Mike, what would you say?
I think Lou hit it right on the head there. That perseverance is very important. You mentioned I have a new book out. I talk a lot about that. Particularly, my new book is meant for young readers. So the reason I wanted to write that was to tell some of the stories, some of the experience I've had related to a young age, having a dream. I had a dream of being an astronaut when I was 6 years old. And I'm old enough to remember Neil Armstrong on the moon. And then as I got older, I thought that becoming an astronaut was impossible. And it really wasn't impossible. I was able to pull it off, but there were times when I felt that way, that it could never happen. But I come to realize that there's a difference between things being impossible or just really hard, which becoming an astronaut or an astrophysicist or just about anything in life is. If you think of my probability of becoming an astronaut, it might have been maybe 1 out of a million, but that's not zero for you math people, right? It's a non-zero outcome. And there's a lot of zeros, but there's a 1 at the end of the zeros. It's not totally zero. And the only way that 1 at the end of it turns to zero is if you don't try or you give up. Once you give up or you don't try, you know what the outcome's going to be. So I think what Lou said is really important. Persevere. Successful people are not those that never fail. They're those who never let failure stop them in whatever you end up doing. So if you're interested in this sort of stuff or whatever you're interested in, pursue it. Don't worry about it necessarily if you're really good at it or how hard it is or easy or whatever. And if it makes sense to you, another thing I thought Lou said was really good is that there's a lot of problems in the world. But if you're interested in this stuff, that's what you're interested in. I think there are many things that are important in this and that we can work on. But for me, it was the space program. That's what I thought was most important. And so you need to accept what you love and say, all right, that's how I'm made. I'm going to go after this and not give up and do your best, and dreams can come true.
Liz, Jennifer, what about you?
Oh, I would say that we need people with all kinds of talents in this whole enterprise of space exploration. I grew up on a farm in rural Arkansas. I didn't really know any scientists. I had no idea how you become a scientist, but I did get the encouragement from family and teachers and community to just kind of go forward and don't sell yourself short. Try things that are of interest. Um, I studied, of course, math and science. I think that's important to try to get as much of those kinds of courses as you can. But also, you need to be diverse in your experiences and talents in terms of knowing how to read and speak, and being able to communicate is really important in these fields. We need scientists, we need engineers, but we also need science communicators and teachers, and we need managers and people who know how to manage the projects and the finances. We need computer specialists. We need leaders in local, state, and federal government who value science and kind of the more creative uses of human resources. So we need lots of talents. We even need artists and poets and musicians to express the beauty of and wonder of what we're seeing. So I would say, build your talents in a diverse range of things that interest you. And as you have opportunity, I'd say also try to get internships. I think that was really very helpful for me as I went on into the university years, getting short-term experiences in different types of fields related to science, or in my case, in related to space exploration. Doesn't mean you're necessarily going to do that particular thing for the rest of your life, but every little experience of working in a lab or working with a professor or working with a science facility can help build your sense of what you're interested in and build your skills. NASA has an internship program. You can look at intern.nasa.gov and find out about that. Early on, when I was an undergrad, I participated in a NASA program 2 summers called the Space Life Sciences Training Program. Now, I didn't go on doing life sciences per se, but that experience really got me excited about doing things involved with space exploration and NASA. So every little internship or experience you have working with someone who's already involved in the enterprise can really help.
Sure. It's funny that you mention art. I'm actually trained as an artist. And the images that have come back from Hubble and Juno have really inspired some of the artwork that I've done recently. So we're getting ready to wrap up. So we've got a couple more questions I think we can answer. Were you all aware of how big a deal Hubble was going to be when you started working on it? Well, let's start with you and we'll go around again.
Oh, yeah. So this has been. I'm young enough that Hubble launched when I was a teenager, and it was highly inspirational. I mean, you could see the transformative nature of this telescope. You could see what we used to get in terms of imaging of these beautiful astronomical images, and what we got from Hubble. And it was such a iconic transformation that you could see these pictures everywhere: T-shirts, mugs, mouse pads. I know that many of you don't know what that is, but a mouse pad, those things. It was everywhere. So when I first started working with Hubble, I was bragging to everybody who would listen to me. It was, my mother and I would just, I use the Hubble Space Telescope. It's a beautiful thing, and it's always been a pride for me to be associated with this telescope.
Mike, what about you?
Well, first, I want to show you my Hubble mouse pad right here.
Perfect.
There's a lot of advantages of being a Hubble mission. So that's my Hubble mouse pad right there. And the Hubble image over my shoulder here. Okay. I was in graduate school when it launched in 1990. And we talked about earlier that it didn't see very well. I was at MIT when that happened, and there was a lot of excitement. I remember first hearing about it before I went to grad school, walking through Penn Station in New York City, seeing a Life magazine cover at the beginning of 1986, talking about the launch of the Hubble Space Telescope, which then got delayed. There was the Challenger accident. And so we were anticipating. I remember hearing about it more through the media, and then as a student, a lot of excitement up at a place like MIT, and then disappointment that I didn't see very well. And then it was corrected. I was starting to work at NASA as an engineer. To me, it was always like the pinnacle. It was, and when I began into the astronaut office, like, this is the coolest mission. that any astronaut could ever dream to be a part of. And so I saw it kind of maybe from like a fanboy thing when I was in grad school, and then when I was working at NASA. And then somehow it just kind of timing worked out that I was in the right place at the right time, that they were looking for a rookie to spacewalk, and John Grunsfeld and others were kind of recruited me, and I was able to get on that mission. So that's when I first heard about it. I was just kind of just kind of dreaming about what it might do someday, and then actually get a chance to put my hands on it was more than I could ever wish for. So that was my first and my last experience with it was up close.
What about you, Jennifer? Did you know it was going to be a big deal?
We did. I was also in graduate school studying astronomy when Hubble was launched. I was learning a different type of astronomy. I was using radio telescopes, but all of us, no matter what kind of telescopes we were learning to use, were excited about this prospect of having a platform for astronomy in space. And indeed, we followed it very closely. And then years later, when I had the opportunity to actually join NASA and work more specifically with the Hubble Space Telescope mission, it was already a famous telescope. And so I already knew that it was big and important. And Hubble is important not only for these groundbreaking or space breaking, I should say, discoveries about the universe, but also because of this really unique aspect of the interplay between astronauts and the observatory. So this ongoing relationship of the human spaceflight program of NASA interfacing with the science programs of NASA in this very real, visible way, where we needed the astronauts to keep Hubble, first of all, to deploy Hubble in the first place, and then to keep it at the forefront of capability. In fact, that's why Hubble is more scientifically productive now than ever before. It's because of this successful series of repairs and upgrades on Hubble. And that interface between the human exploration program of NASA and the scientific goals of NASA's science program is, to me, just fascinating and kept me drawn to this program as particularly exciting. And even now, I find this connection from all these different skills and aspects of space exploration that kind of come together in Hubble to be particularly compelling and inspiring for future missions as well.
We are actually a little over time, but I would be in big trouble if I didn't ask one of our space history curators, David Dvorkin, wants to know, will the Hubble ever be retired? And if so, what will be the future of ultraviolet astronomy in space? So if we could answer, someone could answer that briefly, so, but I would be in trouble if I didn't ask.
Well, personally, I would hope that Hubble isn't retired anytime soon. But as Mike has already pointed out, it will eventually have to be brought down. And so I think that sets the upper limit as to, or maybe it sets a limit as to when we may need to decommission Hubble. But in terms of the future of ultraviolet, there's the time is ripe now to think about what the next generation of space observatories will be like. And that's exactly what the community is doing. We're doing a introspective, if you will, that we do every 10 years to decide what will be the key goals for this next decade, the 2020s and beyond. And it's part of that thinking, we're thinking about what should be the next space telescopes that allow us access perhaps to the ultraviolet. And there's some really great designs out there like LUVOIR that I think will ultimately come to fruition. But those may not be until the 2030s, 2040s, and perhaps beyond. So there will be a gap between when Hubble stops observing the ultraviolet and we're able to resume observing in the ultraviolet.
Well, thank you all so much for joining us today. I'm sorry, we have to wrap it up. I want to let everybody know that our latest version program of STEM in 30 is out today. It is about World War II and Victory in Europe Day. And next week, we will have another live chat at 1 o'clock. And we will have one of our curators, and we will have folks from the National World War II Museum in New Orleans on. So please tune in for that. And you all, thank you so much for joining us. I really appreciate it.
Thank you for
We
having me.
enjoyed it.
Thank you. Thanks very much for letting me participate. This was really fun.
Oh, I'm glad you were all here. This is my all-star team. Thank you.
Go Hubble.
Go Hubble.